as Laura said, I'm going to talk a little bit about exoplanets today. In particular, I'm going to talk about transiting exoplanets. So, exoplanets are stars that exist outside our solar. Exoplanets are planets that exist outside our solar system. They orbit other stars than our sun. And the transit method has become one of the most dominant in the search for exoplanets. But before I tell you how this method works to find exoplanets, I'm going to ask, why do we even look for planets? What are we trying to find out? Well, the universe, it wasn't built in a day. We're not going to see the light and the depth of the solar system. So how do we know how systems form and how they evolve through time? Well, if we can look out into the universe and we can see what stages of evolution different things are in, and we can see what kind of systems exist, we can infer how they got there and how they're going to change with time. But another kind of primary aim of exoplanet research is to find another Earth. So this is the most Earth-like planet we found to date. It has the catchy name of Kepler 452b. So on this picture here on the left, you have the Earth and the Sun, and that's mirrored by Kepler 452b and its star. The stars are pretty much identical. The one for this new planet is just a little bit bigger, and the planets orbit at very similar distances from their stars. So the Earth orbits the Sun at a distance of 1 astronomical unit, and this planet here orbits at 1.05 astronomical units. So it's very, very similar. And this new planet is thought to have lived in the habitable zone of its star for its entire lifetime. That means that it's always had the potential to have liquid water exist on its surface. So this planet orbits its star in 384 days, so just a little bit longer than a year. It's also, as you can see, it's a little bit bigger than Earth. Its radius is 1.6 times that of Earth, so it is a little bit bigger, and for that reason, we're not actually sure if it's a terrestrial planet like Earth. It could actually be a gas planet. But currently, scientists are saying that it is a terrestrial planet with about a 60% certainty. So this planet was discovered by the transit method. So I'm going to tell you how that works. So if you look at the top diagram here, you can see that if a planet crosses in front of the star, there is a drop in the flux. And that is this kind of characteristic light curve, as you can see here. But you're not going to observe a transit for every star that hosts a planet. A consequence of Kepler's laws of planetary motion and Newton's law of gravitation is that the planets in the star systems lie in planes. And these planes are inclined randomly throughout space. So it's a pretty low probability you're going to see a transit if the star hosts a planet. And you really need a configuration like this one, which is edge on, so you can really see what's going on. But if you have something that's kind of like pole on, like here, the planet's going around like this, you're not going to see it cross in front of the star, you're not going to see a transit. So when we observe a transit, what we can measure is we can measure the dip in the flux, we can measure the period that it takes to go all the way around, and we can measure the time of the transit. And from these measurements, using models and data and some computational work, we can figure out the radius of the planet and the star, the orbital period, and how inclined the orbit is with respect to us. Unfortunately, we can't find out the mass of the planet. We can find the mass of the planet if we observe the same system using the other most popular technique. This is called radial velocity measurements. And if we measure from both of these techniques, we can actually find out how heavy the planet is. You can also learn a lot more from transit though. They're very interesting. You can learn about the atmosphere of the planet. So during the primary transit, the light from the star is passing through the atmosphere of the planet. And when this happens, some of the light can be absorbed by the atmosphere. And you can look for possible extinction lines in the spectra. So when you look at the planet in the infrared light, you might look and you might see absorption lines for molecules like carbon dioxide, CO2, methane, things like that. But if you look in the visible light, you might see the existence of metals like potassium and possibly things like titanium oxide. But if you look in the ultraviolet light, you're going to see possible lines of hydrogen and maybe some other ionized metals. There's this thing also called the secondary eclipse. So that is when the planet goes behind the star and you see an additional drop in flux. This is very low probability that you're going to observe both of these, because there's a good chance that the planet's just going to creep over the top of the star or underneath if it's really not edge on. And when you look at the secondary eclipse in the infrared light, you're seeing the drop in flux is related to the thermal emission from the planet. So by looking at that, you can figure out an average surface temperature of the planet. And when you look at this in the visible light, you're seeing the reflected starlight disappear. So you can get kind of a feeling for the albedo of the planet, so how well it reflects light. If it has a rocky kind of shiny surface or a big kind of puffy atmosphere that absorbs all the light. You can also learn about the activity of a star though, which is pretty cool. So stars are pretty crazy things. They do a lot of stuff. They're very active. And they have these things called sunspots on them. These are regions of the star's photosphere that are just slightly cooler, and they appear dark, as you can see here. So if a planet is to cross a sunspot when it's transiting, it's effectively blocking less light. And this results in this kind of little bump in the light curve here, where the flux increases and then decreases again. So by looking at these, you can infer, oh, there's lots of spots, this is a very active star kind of thing. But you can see by this GIF that the spots are moving, and they're traveling around the star because the star is rotating. So another thing you can do is you can look at these light curves out of transit, and you can look at the modulations from the star spots turning around, and you can actually figure out how fast, or the period of the rotation of the star, which is pretty cool. That's what I'm doing for a project this year, actually. Doing. And, okay, this is a lot of dots here. So this is kind of exoplanet discoveries to date. So far, 1,911 planets have been discovered, which it doesn't seem like a big number, but it is quite a big number. So all the green dots are from transits, and all the red dots are from the radial velocity technique I mentioned briefly earlier. So on the x-axis, you have the period of rotation of the planet, so how long it takes to go all the way around. And then on the y-axis, you have the mass of the planet with respect to that of Jupiter. So I put on these two big dots. The black dot is where Jupiter would be, if you put it here, and the blue dot is where Earth was. So you can see we found a lot of Jupiters, things like Jupiter, heavy, but we haven't found as many Earths. It's pretty sparse there. That's for two reasons mainly. One is time. If you're going to look for a transiting planet, you're going to have to watch it go all the way around, like once, maybe twice, 3 times. And that's going to, if you're looking for an Earth analog, that's going to take you 3 years. So you need a lot of dedicated telescope time for that to happen. Another thing is precision. So a typical transit depth, so the drop in the flux when the planet crosses, for a Jupiter-like planet, this kind of current orbit is about 2%. That's pretty tiny. But when you go to an Earth-like planet, the drop in flux for Earth would be less than 0.5%. That is tiny. Like, it's pretty hard to distinguish that from noise. So that's mainly why we haven't found any Earths. So this is kind of just to summarize some of the NASA missions that have been happening. So up here on the left, you see Kepler. Kepler was launched by NASA in 2009, and it surveyed the same patch of sky for almost 4 years, looking for those periodic dips and flux from the stars to account for transits and possible planets. And Kepler was pretty great. It discovered 1,030 exoplanets, so that's more than half of what we actually discovered. And Kepler is still doing some work now, but it's a little bit different because it's kind of broken. It's a bit of a shame. But next, NASA plans to launch TESS in 2018, early 2018. TESS is the Transit Exoplanet Survey Satellite. So the primary mission of Kepler was to search for habitable Earth-like worlds around sun-like stars. But TESS is going to be looking for stars that are a lot closer to us, because closer stars are brighter, so you have better data, basically. Further away, things are a bit dimmer, the noise just kind of gets in the way. So TESS is going to look for stars close around us that have planets in short orbital periods, and that's pretty cool. And then up here at the top, JWST, this is the James Webb Space Telescope. It's also planned to be launched in 2018 by NASA. That might change. And JWST is not solely for exoplanet research. It's going to be looking at distant galaxies, the first stars that formed, loads of things. But in terms of exoplanets, it's going to be looking for, it's going to be doing spectroscopic work. So like looking at planets like Kepler 452b and seeing what is there. Are there molecules that could, are they markers for life? Like what's going on there? Kind of figuring out what's happening. So yeah, that's about it. But if you guys have any questions, I can try and answer them a little bit.
How are you getting your data sets for your project?
I'm going to take the data.
First one at a time?
I'm using data from Kepler, so I'm going to download basically just all of Kepler's 4 years of data from the NASA website and try and figure out how to kind of use that. So it's all online, it's all open source. Yeah.
I think you showed when you were looking for the exoplanets, they give a peak rather than a trough right up to the exoplanet, the actual sun's light. Why is it the case?
And the sunspot. So this,
so
the sunspots are, they appear
dark.
dark because there's a lot less light coming from them, they're colder. So when the planet crosses the sunspot, it's as if, how can I say this, like, it's not blocking light anymore, it's blocking less light. It's covering like the same area, but it's blocking less light because the sunspots are dark. So when it's going there, there's more light. It's like you've taken away the planet for a second and brought it back.
So the planet is kind of lighter than the sunspot?
Kind of. The planet's blocking less light when it's in front of the sunspot. It's like you've like shrunk your planet or something. I guess.
Right.
Yeah. Does that help? But yeah.
So
they're like darker regions. It's as if you just imagine they're completely black. So if you have like a circle with a completely black circle and you cover that circle, it's like 100% of the brightness. But if you pull it back, you're still
So
losing.
if you imagine the sunspot as being like black,
Yeah.
and you put
And you have another
red
planet.
in front of it,
Yeah.
you're picking up the red. rather
Kind
than
of.
black.
Well, most of the planet is just completely blocked out. The atmosphere is very, very thin, so it doesn't count much. Yeah.
You said about radial velocity.
Yeah.
There's another way. What is that?
So on the planet orbits the star, but the star moves as well. They're orbiting around their common center of mass. So when basically the star is kind of moving in a bit of a circle, and when it moves away and towards you, the light from the star gets shifted. So when it moves towards you, the light kind of gets kind of blue shifted, and further away it gets red shifted. You can measure that changes basically.
It's being pulled by the planet.
Yeah, pull back. Yeah.
And recently, like in media, I saw that there was like a lot of hassle because they found a star that had like very weird light patterns, like massive dips. And I know,
Yeah, they thought
I'm
it was
sure
some
you know.
kind of like alien
Yeah,
megastructure or
exactly.
something.
What
yeah.
do you think about that?
I think I read like an article about it. I think it's just crazy system of comets or something. I'm not sure. I mean, like megastructure would be pretty cool, but